So the next speaker is also from EDA, it's Flavien, and he's going to talk to us about microarchitectural vulnerabilities and EDA tools. And Flavien, this talk also is not recorded because it's under review. So Flavien, the floor is yours.
Yes. Okay, so please be attentive because it's not recorded. So I will show you a novel approach to find scalably hardware bugs. And the idea is to find very complex bugs in very complex designs, like your CPUs, for example. My name is Flavien Solt. I'm working with Kaveh Razavi at ETH, and we did the prototyping with Intel. You're probably, some of you, familiar with these logos. They represent critical security vulnerabilities that were discovered from 2018 on. These are hardware vulnerabilities, so they are very difficult to fix, but they are also very difficult to detect in the first place. And bad news, since 2018, every year there is a new flow of new, very critical vulnerabilities that are discovered. It's always getting worse. Is there a way we could do something? Find automatically these vulnerabilities and also find automatically new vulnerabilities that we don't even know about yet. The idea is that all these bugs, at least very, very many of these, rely on information flows, from some secret to some attacker visible place. So let's assume we had this super mechanism that colors some secret data here in orange. We don't see it very well, but there is color here. And let's say there is some privileged, for example, the OS does a load of privileged data. It goes to a buffer, goes to the cache, goes to the core. Now, it context switches to some attacker process, for example. So the secret is not anymore in the registers, but maybe it leaves some state in the CPU dependent on the secret. And then the attacker may try to leak this. But if we have this mechanism, then we could see the leak. And this is something that does not exist yet. At least, it does not exist on complicated CPUs. So here is a table of our results. So the three first ones are CPUs or SoCs in RISC-V that could already be implemented, be instrumented, and on which we could follow information flows. We show that we can do it with 1 or 2 orders of magnitude faster. And we're also the first. We have a new mechanism that allows to do it on any CPU size. So this is very new, and this is what I will present you. Just a little bit of background. How do we do this? We take a CPU, for example, or any kind of design. We keep the same functionality, but we add new hardware that allows tracking the information flow. Let's take an example. This is an AND gate. You're probably very familiar with that. I assume that A is secret, and B is not secret, but it's fixed. So let's do an exercise. B is equal to 0. Now, I am an attacker, and I want to get secret information by looking at the output of the AND gate. Obviously, if B is 0, then I will not learn anything about A, because it will be 0 anyways. Makes sense. If B is 1, yeah, then I look at the output, I get the secret. So now the question is, how do I build something that could follow the secretness? So the first ingredient is to have 1 bit per signal that says, oh, is this bit secret or not? For example, here, AT is equal to 1 means it's secret, BT is equal to 0 means it's not secret. As simple as that. This is something that we add. And then we want some logic that supports propagating this information. So if we do some pen and paper exercise, we get this logic for the AND gate. So for every AND gate in the design, we would need to follow the information flow to add this amount of logic. This is a lot. We could do the same for an OR gate also and for a NOT gate. That's it. This is the state of the art. Now, typically, in a CPU, you don't do just OR gates, AND gates, etc. The programmer uses macro cells. So he says, oh, this is an addition, this is a subtraction. Can we do better? What's happening, actually, when we look at the state of the art? When you want to instrument, like we did, an AND gate or OR gate, for example, then we just break it down into AND and OR gates, and then every single gate like this, we instrument it individually. Let's look at the consequence. If you are a simulator, you will see an addition here. So you're very tempted to just say, oh, let's simulate an addition. That's it, one cycle done. This is how the simulators actually simulate an addition. The problem is, if you want to decompose it first, and then instrument every single gate, then you cannot anymore do this trick. That gains you a huge amount of time. You cannot do it anymore. You have to do this, and this is extremely expensive. And then you get 1,000 times slowdown. Again, this is expensive. What's the solution to that? We've seen that this instrumentation at gate level has scalability problems, because every single gate, you need to instrument it. But it has an advantage. It's complete. What I call complete is that I give you any kind of design, I give you any design, and if you have infinite amount of resource, you can do it. It's just a problem of scalability. But there is no fundamental problem that prevents you from instrumenting something. So some researchers in 2018, so the gate level solution was proposed in 2009, and an optimization was still an open question until now, and that is complete. Some researchers proposed to instrument a higher level, which is the language itself. So typically, CPUs are written in HDLs like Verilog, and they try to instrument this kind of statements. The problem is the HDL, so the language itself is very complicated, so it requires a huge amount of engineering, and no one has done it as far as we know. We show that actually there is a much simpler way of doing it, and this is completely new. This is what I will present. You can do it at cell level. What is a cell? A cell is simply a macro cell, and this is the intermediate representation that is used by virtually all the EDA tools. So all the synthesizers, simulators. It has only less than 30 classes, so we can try to do them, all of them, without looking at 590 pages of specification. And also now the question is, how do we make it scalable? And the trick is that we want to still do the same thing as I showed before. If we have an adder, we want to simulate it as an adder and not as a bunch of OR gates and AND gates. And this will be massively good, you will see. Okay, so this will be a step in our reasoning. I will just take a generic cell, so just a generic combinational block, and I will want to know how does the information propagate here. So let's take an example. This is a cell. I assume that it doesn't have any state. You can see it as an adder, for example, or just as a black box. You don't know what it is. Let's assume this is secret, this is secret, this is fixed and known, this is fixed and known. The question is, what is the output? What output? Sorry, is this output dependent on the secret? Is this output depending on the secret? Knowing these values. Let's do the experiment. I will just put all the secrets. I will give the secret 0, 0. I look at the output. I do it again, 0, 1. Okay, I see that this changed, right? So this output here is actually secret dependent. I continue. Same thing. Same thing. So here you see that it's not secret dependent. I just brute forced, and I see that it's not secret dependent. Okay, what's the conclusion? Okay, I propagate like this. So far, so good? Okay. In hardware, what is really nice is that you can do everything in parallel, right? We just have here 16 instances. Why 16? I showed you only 2 tainted inputs. The problem is you don't know when you synthesize what will be tainted, because this is something that is dynamic. So I replicated 16 times, so I can do all the combination of inputs. So all the C's are exactly the same cell as the original one. For example, if it was an addition, then C is an addition, 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 etc. The only difference between them is the input that I give. So here I force on all the orange arrows to be 0. Here I force all the orange arrows to be 0 except the first arrow, etc., etc., etc. So you have 16 combinations. And then you just compare the outputs. So I just said the gate level is expensive. Now you give me an exponential solution in the number of input bits. So yeah, there's a problem of scalability here as well. But this is just a step to give a good solution. What I will show you is that actually we can do this. So we remove almost all the replica. We just keep 2 of them. So we are not exponential in the input size anymore, but constant. Okay. How do we do that? We looked at what the cells actually do. So we went through all the cells. There is not many, 30, a bit less. And we look at what they do mathematically. And we saw 3 very interesting properties. The first one is bitwise monotonicity. second, transportability, and third, translatability. So look at the paper for a very specific definition of them. I will focus on monotonicity, and you will see that it looks very much like the intuition that you would have, so just increasing functions or decreasing functions. And I will focus on the example of the comparison cell, but you will get the rough idea. Let's look at the example. So here, the first one here is secret, and that's it. If I change it, tack, the output changes. So the taint propagates here, right? This we understood. But if I taint these two, then the taint does not propagate, right? Because I cannot force the comparison to be true if only these ones are secret. Actually, we know that if we increase on the left and the output was 0, then if we increase more on the left, it will still be 0. On the right side is the opposite, of course. If you decrease the outside, then it will still be 0. And actually, you can use this property to make exactly the trick that I showed. So you maximize the left, and you minimize the right. You minimize the left, and you maximize the right, which make two replica. Let's look in images, because it's always easier to understand. OK, so let's have 4. I hope it's big enough. You have 4 input bits that are secret. And I want to know, oh, is the output bit tainted? So before, we need an exponential number of, so we would need 2 power 8 replica, but actually not. We just do this, tack, output 0, tack, output 1, that's it, done. We know exactly which bit is tainted. Path, path, 2 replica. What does it do in practice? This is another, and this is a very reasonable size change. So this is just the input size. How many bits do you actually add? This is the state of the art. Gate level implementation, linear. This is our 2 replica. And this is simulation performance. So if you want to simulate, this is another that you find, for example, in a 64-bit CPU. So this is extremely common. And you see that there is a gap. It's just enormous. I did not choose only the other because it's the other. Let's look at more cells. So this is the state of the art. So again, cell size, simulation runtime. I could not even do the multiplier here because it was exponential here. Cell lift. Constant. The idea is really to try to find something in constant time, even though there was one step that looked exponential at the beginning. So now you probably understand better the reasoning. We did also macro benchmarks to make sure that actually we are representative. So we took 5 CPUs, RISC-V CPUs that are open source. I would say from the most simple to the most complex. So this is a 7th stage out of order 64-bit CPU. I would say quite complex already. We take standard RISC-V benchmarks, and we measure how slower it is if we track the information flow compared to if we just run the normal design, because we still expect some slowdown, right, if we want to follow the flows. The question is how much slower we are. This is it. So we are the first one to actually do the complex ones, and the simpler ones, well, we do them much faster. And also there is a parameter which is called precision that we also improve, but that is out of scope of just this presentation. So this is what we perform on actual designs. There is applications, because now, yeah, you have a mechanism that is fast, that is good. The question is, what do we do with it? So I underlined 4 applications in the paper. I will focus on Spectre. So very simply, Spectre is nothing else than a race condition with the branch resolution. So on a black box, we can say, oh, if the branch resolution is slow enough, then an attacker can leak a secret. This is everything we need to know about Spectre. So if you did not know already. So just let's decrease, up. Branch resolution is still big enough to leak, up. If it's not big enough, well. So the question now is, this was difficult to answer before, for example. Very simple example. Is the window large enough? So typically what we need to do to make sure that it's large enough, for example, is to do some floating point divisions and then to do a branch to make sure that the branch is low enough. And typically I will show that we do not require a cache attack. And this is extremely new. Okay, so I did 2 experiments. The first experiment is I did Spectre with a short branch resolution, so not long enough to actually leak. The second one is one where I use this FPU trick to slow down the branch resolution. The question is, how do we observe that actually this doesn't work, this works, this works in, let's say, something reliable, fast, etc. So I just count how many taints there are. I just look where the secret data went. And this is quite eloquent. So here in a solid line, you see the taint does not propagate. You can also look exactly where the taint is. So here, solid line is constant. Here, I try to do a load to leak. In one of the cases, so in this case, we see a leak. In this case, we do not. So you can underline one thing. We do not need any cache attack or anything like this to see automatically, design independently if spectre happens or not. We can also measure exactly, do I need 4, 3 floating point divisions, for example. So this is extremely useful for hardware designers who know if their design is secure enough against spectre. Also extremely useful for attackers to know if their attack is will be efficient, it will be effective. So you don't need to do too much, but you need to do exactly just the right amount. Okay, it's time to conclude. So we have the first mechanism that instruments complex CPUs can follow information flows in it. We are much faster on the some CPUs that could also be instrumented. Yeah, it also solves problems because if we just have a mechanism that does nothing interesting, it's not so interesting, but we solve a lot of problems. And this is only the beginning of the adventure because this is using it is a major field of research of ours now. And finally, good news, we will release it open source for you. Thank you very much.
Thank you very much, Flavien, for the very interesting talk. Any questions?
So I'm not sure if I understood correctly at the beginning, but it sounded like you were also aiming to detect side channels, for instance, because you mentioned a case where you had a context switch and you could track information going from one context to the other. So how would tainting information on gates allow you to detect whether information is going from one?
Yeah, I will give you, thank you for your question. I will give you an example, which is actually also in the paper. Let's take Meltdown. So I hope okay. So in Meltdown, the operating system, for example, will load some secret data into the L1 cache, let's say. And then an attacker will use a race condition so a hardware race condition to actually leak this data. And this you can follow, for example, very easily with taints. Because your data in the cache will be tainted, and then the taint will be followed, and then you see that the taint is in the register file.
So, but this is still in the same context, right? So
it's context agnostic. Maybe.
Okay, so yeah, we can take it offline.
Okay.
Any other questions? Okay, let me take one then. So this sounds great. Is there a catch? And if not, why not everyone is using this already?
Because it's new and not yet public.
Okay. Cool. Thank you very much. Let's thank the speaker once more.